Hello friends, today we are going to continue normal subgroups. So we have already seen what are normal subgroups and we have seen normal subgroup test also and certain equivalent conditions when a subgroup becomes a normal subgroup. So that was in the previous lecture that we have seen already. Today we are going to just see some more results related to normal subgroups. So let us see first this. You have a subgroup N of a group G, then we are saying that N is a normal subgroup of G if G and G inverse belongs to the subgroup N for all G belongs to G and N belongs to N. So this is the sufficient condition when N becomes a normal subgroup that we have already seen. You have a subgroup N, when N becomes a normal subgroup if G and G inverse belongs to the subgroup. For all G belongs to capital G and for all N belongs to capital N. Now we have some important results, certain necessary and sufficient conditions for a subgroup N to be a normal subgroup. A subgroup N of a group G is a normal subgroup of G if and only if G and G inverse equals to N for all G belongs to G. Now this is necessary and sufficient condition. If you have a subgroup N, and then it is normal subgroup if G and G inverse equals to N, and if you have G and G inverse equals to N, then that N has to be a normal subgroup. So here we were having G and G inverse belongs to capital N. So now we are saying that if G and G inverse, here this is capital N, it was, we were taking some number from it. So now we are saying if G and G inverse is equal to N, then N will be your normal subgroup. And if N is normal subgroup, then this condition will be satisfied. So this is your necessary and sufficient condition for N to be a normal subgroup. Now this is second result. It says that a subgroup N of a group G is a normal subgroup of G if and only if every left coset of N in G is a right coset of N in G. So every left coset is some right coset of N in G. If this condition is satisfied, then that subgroup is a normal subgroup. And if you have a normal subgroup, then every left coset of N in G is a right coset of N in G. So this is also a necessary and sufficient condition if and only if condition for a subgroup N to be a normal subgroup. Now there are some corollaries to this result. So if N is a normal subgroup of G, then this first result says that NA and B. So what is your NA? NA is the right coset of N in G. Here the representative element is A. So NA is a right coset and NB is some other right coset of N in G. So we are saying when you multiply two right cosets, NA and NB, then you get a right coset NAB. Here the representative element becomes AB. So NA into NB is equal to NAB. So how we are going to prove that? Let us see. NA into NB. So here that can be written as N into AN into B. Here AN, you can write it like this by using associativity. So here this AN is your left coset. And as we know that for if N is a normal subgroup, then every left coset is equal to right coset. So I can write AN as NA. So this is equal to N into NA into B. Now this is equal to N and AB. Now because N is a subgroup, in fact it is a normal subgroup. So N will be equal to N. If you multiply a subgroup N two times, then it is nothing but it is a subgroup itself. So NN is equal to N. So this will be equal to NAB. So we have shown that NA into NB is equal to NAB. You are multiplying two right cosets, NA and NB, and you are getting this right coset NAB with the representative element AB. Now we have second corollary here. This is with respect to left coset. If you have two left cosets, AN and BN, then you are multiplying them AN into BN, then you are getting left coset with representative element A into B. So ABN. So you can prove it on the similar lines as we have proved the first part. Now we have another result. It is saying that if you have a subgroup H of a group G, then H is a normal subgroup of G if and only if the product of any two right cosets of H in G is a right coset of H in G. So that is that we have already seen that when you were multiplying two right cosets, N was your normal subgroup, you were multiplying two right cosets and you were getting a new right coset, NAB. So here when you were multiplying two left cosets of N and G, you were getting a left coset of N and G, AB, N. So now this becomes a necessary and sufficient condition for a subgroup to be a normal subgroup. We are saying that H is a normal subgroup for G if and only if the product of any two right cosets in G is a right coset of H in G. You multiply any two right cosets, it is giving you again a right coset. Then such a subgroup is called will be a normal subgroup. So now let us see this example. Here we are saying you have two subgroups N and M. Both are normal subgroups. N is a normal subgroup of G. M is also a normal subgroup of G. Then we are going to show that their intersection, that is N intersection M, is also a normal subgroup of G. So as we have already seen normal subgroup test and some more conditions also under which a subgroup becomes a normal subgroup. So let us see here what we are going to do. So you have two subgroups N and M of the group G. Now when you have two subgroups, then we already know that intersection of two subgroups is a subgroup. So N and M are subgroups. That means N intersection M will also be a subgroup. So that result we have already seen its proof in the previous lectures. You can see from there. Now we are saying that N intersection M is a subgroup. Now we have to prove that this N intersection M is a normal subgroup. So we have to prove that extra condition for normalcy. So now we are taking any element G from this group G and an element from the intersection of N and M. So let G belongs to G and A belongs to N intersection M. So if A belongs to N intersection M, then A belongs to N as well as A belongs to M also. And we are given that N is a normal subgroup of G. So if N is a normal subgroup of G, that means G inverse belongs to capital N. So this was your normal subgroup test. So when you have a normal subgroup of a group G, then this condition holds. G inverse belongs to capital N. So since N is a normal subgroup of G, therefore G inverse belongs to capital N. And since M is also a normal subgroup of G, therefore G inverse belongs to capital N. So that means G inverse belongs to N intersection M because it is in both. So it belongs to intersection. So that means N intersection M is a normal subgroup of G. So for normalcy, we have to prove this condition. G inverse, that should belong to your subgroup. So it belongs to the intersection. So intersection becomes the normal subgroup of G. Now, here it is another example. Here you have a set. It is named as Z. So this set Z defined like this. All those elements of the group G, A belongs to G such that AX is equal to XA for all X belongs to G. So if you remember, this set is this is nothing but the center of the group G. So we know that center is denoted by ZG. So this is your ZG, center of the group G. A belongs to G such that AX is equal to XA for all X belongs to G. Now we have to prove that it is a normal subgroup of G. We have already proved that this Z is a subgroup of G. When we were studying the subgroups, then we have already, at that time, we have already seen the proof of this Z to be a subgroup of the group. So we have to only prove that it is a normal subgroup of G. So for normalcy, that condition that G inverse should belongs to Z, that we have to prove. So for that, to prove that Z is a normal subgroup, you take any element from Z and take any element from the group G. So let G belongs to capital G, your group, and A belongs to Z. So if A belongs to Z, that means by the definition of this set, by the definition of center, if A is in Z, then A should satisfy this condition. AX is equal to XA for all X belongs to G. So if it is satisfying this condition for every x, then it should satisfy this for G also. So this implies that AG is equal to GA multiplied by G inverse. Then G inverse is equal to A, and A belongs to Z. That means G inverse belongs to Z. So this G inverse is in Z. That means Z is a normal subgroup of G. So now we have seen that center is a normal subgroup of a group. Here we have another result which will help you to prove that some subgroup is a normal subgroup or not. So if G is a group and H is a subgroup of index 2, so you must be knowing what is index of a subgroup. Index of a subgroup means the number of distinct right cosets of that subgroup in the group. And in the Lagrange's theorem, we have already seen that how do you find the index. That is, index is given by order of the group divided by order of the subgroup. That is your index. Now, in this result, we are saying that if you have a subgroup and the index of the subgroup is 2, then that subgroup has to be a normal subgroup. So, index of a subgroup is the number of distinct left cosets or distinct right cosets of that subgroup in the group, and it is given by order of G upon order of H. So this you have to remember this condition that if you are taking any subgroup whose index is 2, then that is your normal subgroup. Then there is no need to test that it is. You can directly say that it is a normal subgroup. So here this is an example. Here you have to find a normal subgroup of S3. So S3, you know, S3 is the set of all permutations defined on the set 1 to 3. So S3 is identity 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. And A3, and you know what is A3? A3 is the your even permutations. All the even permutations of S3 is in A3. So A3, we have seen that A3, when you are taking the subgroup of all the even permutation, then that subgroup is the normal subgroup. So here we are saying that A3 is the normal subgroup of G, and you can just verify this by using this previous result where we were saying that index has to be 2 of a normal subgroup. So here we are saying that it is a normal subgroup, and you can verify from that result. What is the order of S3? Order of S3 is 6, and what is order of A3? Order of A3 is 3. It has 3 elements. So 6 upon 3 is 2. That means index of A3 is 2. So index is 2. That means it has to be a normal subgroup of S3. So this is how you can show that using index that a subgroup is a normal subgroup. Now here is another example. Here you have two subgroups H and K. Both are normal subgroups of G. Then we have to show that their product H into K, which is given by HK, such that H belongs to H and K belongs to K. We have to prove that it is a normal subgroup of G. So product of two normal subgroups gives you a normal subgroup. That we have to prove. So H is a normal subgroup of G. That means every left coset is equal to right coset. That we already know. So H is a normal subgroup of G. This implies that GH is equal to HG for all G belongs to G. And K is also a normal subgroup. Therefore, KH is equal to HK for all K belongs to G. So if KH is equal to HK for all K belongs to K, that means KH is equal to HK for all K belongs to G, because K belongs to K and K is a subgroup of G. So this K belongs to G also. So we are saying that this implies that KH is equal to HK. So if KH is equal to HK, this implies that HK is a subgroup of G. And this here, this is from this result that we have already seen that H is a subgroup of G and K is also a subgroup of G. Then HK is a subgroup of G if and only if HK is equal to KH. So product of two subgroups become a subgroup if and only if HK is equal to KH. And here we have shown that HK is equal to KH. That means HK is a subgroup of G. So we have seen that HK is a subgroup of G. Now we have to prove that it is a normal subgroup of G. So we have to show that HK is a normal subgroup of G. For that, you consider an element from the group and an element from the product. So let A belongs to HK. So if A belongs to HK, that means A is of this type, H into K, for some H belongs to H and K belongs to K. So therefore, GAG inverse will be equal to G into HK because A is equal to HK. So this will be equal to G, HK, G inverse. Then this can be written as equal to GH, G inverse into GK, G inverse. So this thing belongs, GH, G inverse belongs to your capital H, the subgroup H, because H is a normal subgroup. So this should belong to capital H, and K is also a normal subgroup. So this should belong to capital K. So this belongs to H and this part belongs to K. That means this whole thing belongs to HK by the definition of HK. So this GAG inverse belongs to HK, and hence HK is a normal subgroup of G. This is the condition for normalcy. So HK is a normal subgroup of G. So in this lecture we have seen a few examples of normal subgroups and certain conditions for normalcy of a subgroup. And when do we say that product becomes a normal subgroup? So these are certain conditions. The product of two right cosets is a right coset that we have already seen in this corollary. So this was all about normal subgroups. So this was in continuation to the previous lecture. There we have defined normal subgroups. Certain examples were given in that also. So I have continued that thing in here. So in the next lecture, we will be seeing the factor groups. So for studying factor groups, normal subgroup should be clear to you, because a factor group you cannot understand factor group without the normal subgroups. Factor group or is also called the quotient group. So if G is a group and H is a normal subgroup of G, then factor group is G upon H. So for G upon H, H has to be a normal subgroup. So now you have seen normal subgroups, certain conditions for and equivalent definitions also, conditions also for a subgroup to be a normal subgroup. And you have seen many examples now. So I think normal subgroup is clear to you. So in the next lecture, I'm going to continue that factor groups. So hope you like it. See you in the next video. Thank you.